First, I will thank the organizer for organizing this meeting. So I will talk about some homogenization phenomenon that occur when approximating PDE at stationarity with individual based model. But I will stay at a very informal level all along. This is works that we made with Vincent Calvez, Sylvie Méléa, and Ditran Viet. So the original idea was to take a look at a population that is structured by some quantitative trait X. But you assume that there is an unique optimal trait which is evolving with time, is changing position, and you assume that the non-optimal traits experience a very strong disadvantage. So I shouldn't have written that, but as the inverse. And you want to do the following thing. You want to sample someone in the population at time big T, and he has some trait, and you ask what was the trait of its ancestor backward in time. So to do so, we take a PDE model where you have some function u of t and x, and which describes the density of individual of trait x at time t, and you assume that this function is given by the following dynamics, which we have here. So you have a diffusion which can be assumed to model mutation of or spatial motion. And this is the only way for to transfer mass from some trait to another. Okay. To that, you add a birth rate for individual of a given trait. So they give birth to other individual with the same trait at rate 1. And more important, they experience a death rate which is quadratic with the distance to the optimal trait, which is CT. And to that, you add a computation term of logistic type, which depends on the overall mass of the population, which is here. Okay? So you want this equation to become autonomous, so you make a very easy change of variable by taking the frame of reference of the moving trait, and this just add up some drifts, and now the optimal trait is fixed at 0. So an important feature of this equation is it has a stationary distribution, which is given by this, which is proportional to a Gaussian with the mode at minus c, which is the speed of drift of the optimal trait. So if I draw a little picture, if you have time here, a trait here. So you have the mode minus c here. You look at some time t. And since you assume that the population is at stationarity, almost everyone is around here, roughly. And if you, okay. And if you look at time 0, the picture is the same, so everyone is around here, because Gaussian has a very strong decay away from C, from minus C. And the question that you ask is, I sample someone in this population at time t, so likely it will be someone around here. And you ask, where do you come from? What was the trait of your ancestor? And at the time Vincent asked the question, he had some simulation and computation that suggested that the backward path of the trait of the sample individual was something like an Ornstein-Uhlenbeck process. So something which looked like that with some random perturbation around it. And of course, it doesn't really make sense to just say, I will sample an individual in a population at macroscopic scale. So you have to use a trick to give sense to all that. And the very natural things to do is, well, I can approximate this equation with an individual-based model, and I will sample in this finite-sized population. So I sample in a finite-sized population given by an individual-based model. I can make a sense to these ancestral trajectories of the type of the individual, which I will call y of S. And you take the limit in large population to get back to your PDE and ask what does these things become when you take your limit in large population. The problem is that this equation is nonlinear, and so do the individual-based model, which is the approximation of this equation. And for such nonlinear branching processes, it's quite hard to study the law of such an ancestral path. But you have this following property. If you plug f into this equation, the integral becomes constant, and you see that this equation, this function f, also solves some linear version of our equation. So you take this equation, which is linear. You can do the same procedure as you wanted to do on the other one, but here, when you approximate this equation with a system of particles, this system of particles is a linear branching process, for which we have many tools to study such ancestral paths. Okay? So, we will have two models, individual-based, for the two equations here. So we have two microscopic populations with the following dynamics. So you assume that you have a finite initial population of size of order k. K is our scaling parameter. You assume that the trait x, y of t of an individual y, not y, e. Sorry for my English, it's terrible. And Vt, it's for me the set of alive individual at time t. Okay, so every particle is moving according to a drifted Brownian motion. Okay, drifted Brownian motion because my conservative term in my equations are drifted diffusion. Okay. To that you add binary continuous branching, that is when a particle gives birth at rate 1, the two children start from the same trait as the parent, and a natural death rate of x squared over 2, which say if a particle go away from 0, it will experience a strong death rate. To that, you add two cases. The first one is an additional death rate of the size of the population over k. It's the counterpart of our first equation, with you have a death rate which is the overall size of the population. And the second case is you just add a constant death rate of size lambda. And you so have two cases, a population that I will call Z, the nonlinear case, and a population tilde Z, the linear case, which is the easy part. So when you have such population and you want to approximate your PDE, the natural object to look at is those objects that I call Z T and tilde ZT, which are point measure on the space of Trey, which make mass on the position of the individuals which are alive at time t. Okay, and Z tilde Z is defined accordingly. Okay. So the result, which is quite classical, is not so quite classical. Okay, you assume that your initial condition, once renormalized, converge to the common stationary distribution of your two equations. Okay? So in the IDE, you are going to approximate the common stationary solution of those two equations here. And so the first one, its nonlinear term would just become lambda, the integral of f. So what you expect and what can be shown is that the two processes, Z and tilde Z, the distance between these two in some measure sense, uniformly in time, and you renormalize your processes, goes as the large population limits to 0, which means in the large population limit, my two processes look the same, the linear one and the non-linear one. And the other part is that if I take one of these two processes, they approximate uniformly in time the stationary distributions that you expect. The problem is those processes, and this is seen here, carry very few information about what we are interested in, which are the ancestral linear path. It doesn't contain this information. So you need a richer object than the usual ones, which are known and which are called historical processes. Historical processes are exactly similar to those that I just introduced. The only difference is at time t, my historical processes h of t, which correspond to the nonlinear case, is a measure on the path space of in the trace space. Okay, so unlike making a mass on the position on the individual, I put a mass on the whole trajectories of the history of the individuals. Okay, so x s of the individual e will be defined as the trait of the ancestor of e if the s that I take comes before the birth date of my individuals. And you have exactly the same results. That is, when you approximate your stationary distribution, both processes become the same, and you will be able to compare the ancestral path in the nonlinear case to the ancestral path in the linear case. So here is the strategy summarized. You sample uniformly individuals in H T and tilde HT. some time t. You look at the ancestral path of the selected individuals in time. You study the law of the time reverse process in the linear case. And as the limit in k comes in the game, you hk and tilde hk become similar, and you show that so does the ancestral path. Okay? And for the remaining of the talk, I will only discuss the second point, and we will see that in such asymptotic, there are interesting homogenization phenomena that occur when you look at precisely the time reversed process, the time reversed ancestral path. Okay? So I don't have many time to go into the detail, so I will just say what can be obtained. It's mainly using the results of Aline Marguet in 2019. And it says the following: in the asymptotic where the initial population goes to the stationary distribution of PDE, the law of the ancestral path goes to the one of the time inhomogeneous Markov process, tilde y, with some initial condition, which interestingly is not f, as one can expect, but some perturbation of f with a certain function m of t. So first, let's look at the first point. So, in fact, when if I sample in the population at time 0, I will I will find the distribution f. So everybody is here. But if I sample at time 0 individual depending of the descent at time big T, this induces a bias due to the selection because those ones are far from the optimal tree, they are likely to die before reaching time T. And so the ones which are highly represented in the descent are those who are close to 0. Okay? So this is the first thing to learn in this first condition. And you can have the dynamics of these processes, which is a non-homogeneous semigroup, which is a perturbation with the same function m of t of what is called the Feynman-Kac semigroup, which has this form. And what should be read here is, so X is a drifted Brownian motion, the single particle motion, okay? And you take your single particle motion, but you add a weight, an exponential weight, which depends of the whole trajectory upon time t, and put a very little weight to trajectories which goes far from 0. Because of this term, if my trajectory goes far from 0, I will put a very little weight here, and so this trajectory is very unlikely to be sampled. Okay? In fact, this is almost the semigroup of a drifted Brownian motion, which is killed at this rate. Okay? And in fact, the additional perturbations that you add here, where MT is in fact just this semigroup evaluated at 1, is related to the fact that you condition this killed Markov process to be alive at time big T. Okay. So you killed your Markov process with that, but you condition it to be alive with those a bit mysterious. They are not mysterious, but as I give you this just like that, it seems mysterious. So these terms are just here to condition the process to be alive at time big T. So the good point in this situation when X is a drifted Brownian motion is that everything can be computed explicitly. Everything, that is, we can compute m of t, and you can note that m of t involve 1 over f here. So when I take this. I just have the other part, which look like a Gaussian if big T is very large. Okay, so the distribution of the tray at time 0, if of the tray of individuals having descent at time big T, if big T is big, is almost a Gaussian around 0. Okay. And more importantly, you can compute the SDE which Y satisfied, tilde Y satisfied, which is this non-homogeneous SDE. And using the same method that you will do to compute the law, the first marginal of an Ornstein-Uhlenbeck process is when you when you take this initial condition, you can compute that the first marginal of tilde Y is just a Gaussian with those parameters. Okay. Why is this important? This is important because when I want to time reverse this thing, I need to be able to have access to that and to that. Okay. Why? Because we will apply a theorem of Haussmann and Pardoux for a diffusion tilde Y with a non-homogeneous drift, but a fully homogeneous diffusion. And some hypotheses on the drift, but we don't care. The time reverse process at time big T is also a diffusion when you have the time reversed drift, but you add up the log derivative of the density of tilde Y, the density with respect to Lebesgue measure. Okay? So let's compute that. So we remember that the density of tilde Y is Gaussian. So the log is simply that. Take the derivative, just cancels out the two. Okay. Add up the time reversed drift. We obtain that. And what's happened? So remember, the time reversed drift is just these things evaluated at T. Okay. So what's happened is you have the time reversed drift, the log derivative of the density, and you see that almost everything cancels, and you have the so-called Ornstein-Uhlenbeck miracle. That's the drift in the reversed diffusion is just X. So the diffusion, the SDE, which is satisfied by the time reversed process, is just this one. So the conjecture of Vincent was true. When you at stationarity, when you time reverse the uniformly sampled individual in this population, you get an ancestral path that is an Ornstein-Uhlenbeck process. Okay, so a very natural question that is that's come now up is: does these results depend of the incredible symmetry within the Brownian motion? The answer is not at all, and we will have a very few time to see that. But to answer this question, we need to abstract the problem. So I take everything the same, but the motion of my particle are now not drifted Brownian motion, but some Markov process with generator L and some group P. And you take the new equation, which is the same as before. You do exactly the same as before, but your conservative part is just the formal adjoint of L. So you have this equation. Okay, I don't say that is well defined. Huh? It's just very rough ingredients for what is happening here. And you will assume two things. First, you assume that L star generate a Markov process X stars with the property, some duality property, which we have here, where these brackets here are just the integral of fg against the Lebesgue measure. Okay, so some duality property. Why is that? Because in the deterministic case, you expect to be this to be related to the time reversal of what is happening in your model. And the second big ingredient is you want this equation to have a stationary solution, because you can't reach stationarity at a large population if it does not. But these are two just main ingredients. There are many, many things to be checked along the way, but they are the essential ingredients. And the formula that I gave for those formula are essentially the same for whatever the process X is. Okay, so I can almost do everything like before in this case. So I have that. And an important point is that the famous Feynman-Kac semigroup, when I applied it to X stars, it is known to solve the associated equation here. Okay, so in fact, big F, my stationary solution, is invariant by the action of this semigroup. Okay? And unfortunately, I will have no time to go further, so I will just give the. It's not a theorem because you have to check everything, but we checked these for in two cases. The first case is the one that I described precisely before, the drifted Brownian motion, where your dual process is just the Brownian motion with the drift in the other way. Remember that this is a property in law, so yeah, I don't care. It's if it's the same Brownian motion in both sides. The stationary solution was explicit, and we also checked with Sylvie Meller et Titran Viet that everything works in the case of jump processes with some drift. The dual processes in this case is the operator, the Markov process with generator who has the inverse drift, and the jump are just those who you have reversed the density of the first generator, but you have to make assumptions in order to have that to be the generator of a Markov process. And the existence of S, we just use ad hoc results from Chloé Gabriel to obtain it. And in this case, you show that the semigroup of the time reversed process is just given by this formula, which is a time homogeneous semigroup. And even if if forward in time you have a non-homogeneous Markov process, backward in time you have this homogeneous thing. And we can compute its generator and characterize its law. Thank you.
Thank you, Benoit. Is there any questions?
Thank you very much. So do you have ways to describe genealogies of more than one individuals, like the rate at which they merge, or if you were to sample more than one individual at time capital T?
We were thinking about way of doing that, but it's not done.
It's not done or it's not feasible.
I don't know if it's feasible. Not yet.
Other question?
Hi. So thank you. It's really, really nice. I just have one question about your expression. So you know exactly the path. And so do you have any idea the time to go back from -c to 0? The typical time?
So in the Ornstein-Uhlenbeck case, yeah. So what you call a typical time is some estimate on the probability to be at some distance of 0 at some times. Yes, I think it's totally known for Ornstein-Uhlenbeck process. But if I do that, it would be just the repetition of people from back in time who already did that. But it's doable.
Okay, it's doable. And for the second case, do you think it's also feasible?
Well, your question is related to what is called scale function of Markov process. It's quite hard in full generality to have a explicit expression of the scale function. So I guess it will depend of the kernel M you have here, if you can do that or not. But we didn't try to grasp such information.
Thank you.
Other question? So maybe we'll thank again Benoit.